So this BISH Bash event is brought to you by University of San Francisco. And the agenda for today is, after the welcome, I will request the FAR to talk a little about BISH Bash. It will be followed by the talks and Q&A, and finally networking. The FAR, please let me know when you're ready. I can switch the slides for you.
I'm ready. I'm hearing somebody else talk. Is there somebody else trying to say something? No? Okay. All right. So I think many of you are already familiar with what BISH Bash is, but now we have new people coming from all over the world thanks to the virtualization of BISH Bash. So what is BISH Bash? Originally, BISH Bash was made still. It's an informal networking meetup that was originally physically hosted by technology companies or institutions. For people who are working or are just interested in audio signal processing, analysis, and all the related fields. So we had all those companies that you see on your screen that hosted this event in the past once or a couple of times, even more back in the days. And yeah, we had our first, following that, the whole pandemic thing, we had our first virtual BISH Bash happening a few weeks ago, thanks to Descript and Lyrebird, and it worked very well. So we thought we can continue to do that. And originally wanted to have this this event at the University of San Francisco physically, but that didn't happen. But we learned how to do that virtually now, and I'm happy that people can join us from not just San Francisco. So that's nice. Can we go to the next slide? All right. So. The whole point of BISH Bash is basically, as Arshiya said, you're here to learn about the latest advances in this field, in the field of audio signal processing, analysis, and related fields. You're also here to, I mean, you all have your own wisdom. You're also here to share a bit of wisdom, but also, yeah, have fun, make new friends. I mean, originally those were hosted physically, so we had food and drinks, which was very fun. But I'm sure you can get a beer in the fridge if you want to keep this fun. And I believe we'll have, to try to keep that socialization happening after the presentation, we'll have also, we'll be separated into groups in, the Zoom breakout room. So we'll be able to, talk to a smaller group and maybe ask questions to the presenters, in a smaller group. Next slide, please. Okay, so this will work only if you spread the word. Keep the momentum going. If you want to host this, the next meetup, this is very easy now. We don't need a location. You don't need to buy a beer or pizza this time. Just let us know. We only need like a Zoom account. You let us, me or the other co-organizer of BISH Bash know, and we can have one setup. And as you can see, this is popular, so you have many people coming up. Especially we have like awesome talks like this. You can join us online. You already know the BISH Bash meetup website. But we're also on LinkedIn. Just search for Bay Area's Innovative Signal Hackers. And we also have a Twitter account. The next one, please. And we are not only in the San Francisco Bay Area, but this is happening also in Tokyo and in Paris. So we had, as I said, it all started here in the Bay Area. We had 23 physical meetups hosted since 2013, and our first virtual meetup was hosted this year. Tokyo started its own BISH Bash this year, and while they wanted to host it physically, it didn't happen. So they had their first virtual meetup hosted by Line, and I heard that it went very well. And Paris had also their first BISH Bash this year. They had the chance to host it physically. It was hosted by Deezer this year. So I'm still talking to some friends to see if this can happen in other cities. Perhaps New York or London. And if, again, you would like to try to expand this to other areas in the world, especially underrepresented regions, just let me know and we can try to see if we can help. And I guess that's it. And I'm going to let Arshiya rest. And also, yeah, I would like to thank Arshiya and for doing this, that she did a great job. I don't think people have questions for me. We can move on maybe.
If there are any questions, please feel free to either post them in the chat or speak up or raise your hand. So, all right. Well, at this point, this is the time where we start with our presentations. There are going to be 3 presentations by researchers from Northwestern University and Google Brain. After the presentations are done, that's when we're going to get into the informal networking session. Our presentations are going to be 20 minutes long, followed by a 10 minutes question and answer session. So if you have a question, you can either wait till the end of the talk or you can ask in between, but please ask only relevant or clarification questions in between. If there's a more philosophical or more general question, please wait for the speaker to finish. So let's begin. Let me introduce our first speaker. First speaker is Professor Bryan Pardo. Professor Bryan Pardo is the co-director of Northwestern University HCI and Design Institute and head of the Interactive Audio Lab. He has authored over 100 peer-reviewed publications. He has developed speech analysis software for speech and hearing department of the Ohio State University, statistical softwares for SPSS, and has worked as machine learning researcher for General Dynamics. He has collaborated on and developed technologies acquired and patented by companies like Bose, Adobe, and Ear Machine. When he's not doing all of that, he performs on saxophone and clarinet with bands like Son Monarca and the East Loop. He will be talking to us today about his research on Cerberus. It's a system for music score separation and transcription. Professor, we welcome you. Please feel free to share your screen. I'm going to stop sharing now. So whenever you're ready.
Okay. Well, I recently was on a talk where the person before me ran twice as long as he was supposed to. So I just started a timer so that I will make sure I let the other people talk, because I want to hear, for example, about the Bach Doodle. As you've already said, I'm Bryan Pardo from Northwestern University. And hang on, let me just share my screen as suggested. Sharing my desktop. Can you all see my screen now? Somebody? Yes? Okay. So I'm in computer science at Northwestern. And just for those of you who don't know, Northwestern University is actually in Chicago, Illinois. And even though I'm hanging out currently at Berkeley and giving you a talk from the Bay Area, normally I spend my time in Chicago. Now, as was pointed out, when I spend my time in Chicago, a lot of that time is spent on music. So I want to sort of start off this talk with a song that'll be kind of an organizing principle here. So this is Oh Darling by the Beatles. Okay, great. So one of the things I often do when I am looking for something fun is I will go onto YouTube, find a song by some band that I like, and start to learn the parts. And one of the things that would make it easier for me to learn the parts is if instead of having to pick out the guitar part myself over and over with repeated listenings, what if the guitar part could be pulled out for me by some sort of automated process? Or even better, what if it could be pulled out and transcribed for me by an automated process? So I could do mixing and mashing up with other things. So I could maybe put it through notation software. So I could learn the guitar part and play along. I mean, for vocalists, they've already done some of this kind of stuff where, for example, here's a karaoke version of that song. Right, so if I want to do the play along thing without the vocals, they've done that for vocalists, but usually the way that gets done is it's actually re-recorded. This is not the original recording. For most songs, most pieces of audio on YouTube, on the web in general, you don't have access to the unmixed original tracks that went into the song. And so I would love to have something that gives me that kind of access so that I can do all the things I would like to do with it. and that is what Cerberus is about. Cerberus was a paper presented at ICASP recently, and the first author on that is Ethan Manilow, a doctoral student in my lab. Prem Sitharaman is a postdoc who is actually about to start at Descript in about, I don't know, 3 weeks or so in the Bay Area. And then that little picture is me, Bryan Pardo. And Cerberus is named for the mythical dog of ancient mythology that had 3 heads and guarded the underworld. So what is Cerberus? What does it do? Well, people have worked on transcription systems before. People have worked on source separation systems before. There are whole genres of research about these things. But to our knowledge, this is the first system to transcribe and separate multi-polyphonic instruments, that is, instruments that can play more than 1 note at a time, and percussion all at once. So we're trying for the whole enchilada here. Multiple instruments, each instrument can have multiple notes. They might be harmonic, they might be percussive. Most of the existing work has looked at separating out just the voice, which, for example, would be a single line instrument that is harmonic. Well, it's got percussive elements too. And so this is what we're going for. And the approach we're taking, as many people are these days, is a deep learning approach. So the general structure of the input-output of Cerberus is shown before you on the screen. We take as input a mixture of audio, such as the song you heard, and that is represented to the system as a magnitude spectrogram. So everything that the system is doing is working on a time frequency representation, like this thing that says mixture at the bottom of the screen, where the vertical is time, the horizontal is, the vertical is frequency, the horizontal is time, and then brightness tells you the strength of some sinusoidal component at that time and frequency. So each pixel in this image corresponds to 1 or more time frequency points that we analyze. This goes into a BLSTM, a bidirectional long short-term memory stack. And then this outputs a representation that goes to 3 heads, which is where we get the name Cerberus, 3 different end bits. And each of these outputs something different. The separation, the one we're calling the separation head, outputs actually a mask on the time frequency representation. I'll describe that later. The deep clustering head takes the time frequency representation and embeds it in a 20-dimensional embedding space. We'll talk more about that. And then the transcription head outputs 88 note transcriptions. That is to say, the vertical dimension here is 88 pitches that are available on the piano keyboard, every musical half step on the piano. And for each one of these heads, for the source head and for the transcription head, I should say, it's not just a single source and not just a single transcription. It's going to be the number of sources times the transcription. So if there's 4 sources, then you'll get 4 transcriptions. And each transcription might have multiple pitches concurrently. Similarly, for the mask inference, if there's 4 sources, 4 masks. The structure of the network itself is fairly straightforward. It is 4 BLSTM layers, 300 units each, going to relatively lightweight heads, a single fully connected layer with sigmoid activation functions for each one of the 3 heads. The system uses a 3-headed loss function. And the 3-headed loss function, what it does is it penalizes the system for making errors in either creating a binary or soft time frequency mask, a declustering representation, or a transcription. And the amount that it's penalized depends on, for any one of these tasks, depends on a weighting scalar that you see here, like beta, alpha, or gamma, that determines how much the system is learning from error on any one of the tasks. And this allows us, if, for example, we set alpha to 0, then the deep clustering loss is ignored and the thing learns to separate one way and transcribe another way, and it ignores deep clustering. Now, before I get too far in how all of this works, it occurs to me, maybe you want to hear a little bit of how it works because, you know, your time is valuable and this time could be spent politely looking at Instagram while you wait for the my talk to run out if it's not all that interesting, and then you can pick up the next talk. So let's go to some output. Now that you kind of have an idea of the input and output, and it's got 3 losses, etc. So here what we're going to do is we're going to take that karaoke version of Oh Darlin' and pump it through Cerberus, getting out 4 different tracks: guitar, piano, bass, and drums. So that's the input. This is, let me just freeze that. This is a transcription that you see down here, piano roll style transcription, where the vertical is the piano note, the horizontal is time, and the color indicates which instrument. This is a transcription of the audio resynthesized with, you know, synthesized piano, bass, drums, the whole works. Now you're going to hear that, and then you're going to hear isolated instruments where we take the original audio, put a mask on it to isolate just the guitar, and then after that you'll hear a transcribed guitar, and it'll go like that. Okay, since I'm already halfway through my allotted time, let's keep going. As I said, there's 3 loss functions. Let's start out with the mask inference loss to see how it learns to do the separation here. So we trained this in a supervised manner, and that means that we took audio for which we had already got the separated individual instrumental parts and turned those into magnitude spectrograms. So then what you can do is you can compare that magnitude spectrogram to the masked version of the mixture. And what do I mean by masked? The network outputs a soft time frequency mask where each point on this thing is a number between 0 and 1 that indicates how much of the audio at that time and frequency in the mixture of audio, how much of the audio belonged to that source. And then you element-wise multiply the mask by the spectrogram, and you get back our estimate of the true source, which we can then element-wise compare to it. And Zafar, if you don't remember these, I actually grabbed these pictures of the
I recognize them.
yeah, from the lecture notes he made when he was a TA for my class. So thank you, Zafar.
Great beard, by the way.
And yeah, you look good in a beard. The transcription loss is something extremely similar. We have a true transcription, and we element-wise compare that to the transcription estimate output by the system. And again, this is a straightforward loss. Deep clustering loss is a little harder to explain. If you've got the mixture spectrogram, where again, we've got frequency on the vertical, time on the horizontal, and the redder it is, the louder it is. Let's zoom in on a point, or a subpatch, I should say. And I'm going to zoom in even further because for my illustration, it was too much to try and handle that whole patch. So let's take a sub-patch. So now we've got some portion of the spectrogram. We'll call that X. Now for any particular portion of the spectrogram, since we assembled the mixture ourselves, we know for each time and frequency point whether, for example, the piano was the loudest thing or maybe the drums was. And here for this example, I'm using a binary representation, so we can think of this as a one-hot encoding for those of you who are used to that terminology. And we fire our spectrum, or our spectrogram, I should say, through Cerberus, getting out from the deep clustering head an n-dimensional representation, where I have each row here is an n-dimensional representation of a single time frequency point in X in the original spectrum. Now, I said it was a 20-dimensional thing, and it is in the real thing. I just didn't want to draw a matrix with 20 elements in it, so I drew one with 6. So then our loss function is slightly different here. For every pair of time frequency points represented by each time frequency point now represented by a vector, we can do an inner product between the vector for one time frequency point and the representation for another. And then we can do an inner product between the true labeling. This could be a true binary, or yeah, a true binary mask, or it could be a true soft mask. And we can see the difference between the inner products, where the idea is the inner product between the two representations of the time frequency points should be similar to the inner product to the actual true mask representations. And if they're not, we need to change. And yes, I understand that this requires a normalization procedure in it as well for it to work out. And I just bleeped over that for time. Okay, I mentioned that the thing is actually trained in a supervised manner. And some of you who are savvier in this might ask yourselves, well, sure, I can get lots of recordings of bands playing stuff. That's not actually the harder part. The harder part is getting the transcriptions, the exact transcriptions of what they played. And the way that Ethan decided to go around fixing that is to make the training data from MIDI files. And so what he actually did was he took the Slakh MIDI data set and grabbed 2,100 songs from it. And for those 2,100 songs, he made synthesized versions of it using high quality professional audio synths to make mixtures where we have the exact transcription because it was made from a MIDI file that we know exactly, and the exact separated source because it was synthesized. And then he could mix and match all of these things together in a variety of ways for any particular kind of network to generate guitar, bass, piano networks, or violin, trumpet networks, or anything you want. And each net was trained with roughly 28 hours of training data, 20,000 5-second long examples. Training was terminated when, as is typical, validation loss starts to go up, and that was on a validation set of 4 hours of audio, 3,000 examples, and then holding out 1,000 examples for testing. Now, since we've got 4 minutes left, I do have some numbers and experimental results, but I think it might be more interesting to take a look at some more audio. So if in the questions it goes that way, we can turn to the numbers. But what I want to do now is take you to the Interactive Audio Lab website, where, go away, you're blocking my view of the tab. Okay. Where we've got a bunch of other examples that we can just have a look at, listen to, and you can get a better feel for how Cerberus works on stuff. So here's a video, for example, of Fred Hirsch and Bill Frisell playing the jazz standard Wave. And you can listen to, let's say, listen to the transcription. Or maybe some separation. And there it lost it, and now the guitar is starting to fall in with the piano. This is one where it's trained on guitar and piano, but then tested on violin and piano. So it was never trained on violin. And of course, let me reiterate that the stuff it was trained on is synthesized. It wasn't any real guitar. It was all MIDI guitar. So there's some separation output. Here's the remix. So it was having a little trouble getting some of the piano there. What's another good one? Oh, maybe this. And there's separation. And there's the piano. Okay, I mean, there's a lot of examples here on the web page, and actually, let me point you out where that web page is. If you go to interactiveaudiolab.github.io, you will find that page, and you will find a lot of other stuff on a lot of other topics. And since I think we're exactly at 20 minutes, I'm going to stop there so that we stay on time, and anybody who wants to ask some questions can ask questions. And for the moment, I'll leave this up so that anyone who wants to get to our website, see more examples, read the paper, can do so. This is the part where I'm done, and now if you want to ask questions, feel free.
Do we ask questions via chat or do we just jump in?
You can jump in at this point, or you can put it in chat if you want me to ask.
Well, I already jumped in, so I might as well.
Yeah, what a great idea. Instead of screen sharing that, I am going to stop my screen sharing so that I can put our website in the chat.
Cool. Well, while you do that, I'll ask. So thanks, first of all, thanks for the talk, and very cool results there. So one thing I noticed is that for for transcription, there's always this issue where even if the notes, the pitches are correct, the timing always seems, the timing kind of seems a little fidgety. And then even if you get like a really good transcription in terms of pitch, just having every note be a little bit off kind of really throws you when you listen to the synthesized MIDI. Now, I know that we all love our end-to-end system nowadays, but have you considered, given that it's music, imposing additional structure via, things like tempo, or all the other inherent structure that we know exists in music to kind of constrain the MIDI notes to give something more coherent temporally?
I am super confused. What is your background? Sorry, I was distracted by that. So yeah, sure, we've definitely thought about all that stuff, but I mean, I like to think of it in terms of B.F. Skinner for a moment. So in Skinnerian psychology, there's this idea that everything is just stimulus response. And until you can prove that you can't solve the problem with stimulus response, you don't try any additional work. And so I think sort of where we were coming from it was, what can we do with this? We started with some ideas that came out of Merle, a lot of it, like this work built on top of things that had been happening there for source separation. And, in discussion in the lab, we're like, can we turn this also into a transcription at the same time? And so as we go along and we discover these errors, the first move we make is to improve or change the loss function. So one of the things that we're already doing in the external measure of error. It's like there's two of you. One of these things we're doing the external measure of error is measuring node onset and node offset as explicitly things that we are penalizing. And one could first start to introduce that stuff into the loss function. And then, you know, another thing that we've been actively discussing also in our generation work, we're doing some stuff that's related to the Bach chorale generation, is how do we make an evaluation function that is explicitly penalizing all sorts of musical things? Are you using rhythms typical of the style? Are you using harmonies typical of the style? Are you using node onsets that are happening on strong beats as opposed to off the beat? And of course, it'll all be style dependent, because if you have something that favors being on the beat and then you hand it some funk music, it'll run into problems.
Cool, thanks.
Hey, Bryan. That was an awesome presentation. I also enjoyed that you used a Python notebook, I think a Jupyter notebook for the examples in the end.
Yeah, well, that was Ethan used it. So I think he's probably on this thing right now. So you should praise Ethan.
Nice. Yeah, I was curious about the embedding space that you learned. One of the heads of the Cerberus, and I was curious about how much weight did you have to add? Like, how much did it add to the whole process? What happened if you removed that? How much did it influence the quality of the whole thing?
Excellent question. So how much time we got? I got 2 minutes. Okay.
Yeah.
So a question is, does co-training help? And if we've got this, could we train the network just to do one thing, or just deep clustering, or just transcription, or maybe combinations? And the answer is, we did actually look at that. And the short story is, we tried training the network just with the mask inference head, just to do source separation. And here's some example data on how well it did source separation. Since we only trained mask inference, the output of the transcription head was meaningless in this case, so it says NA. But you can see it has an SDR of about 6.2. Numbers in parentheses are standard deviations. Just deep clustering got 5.7. We'll skip transcription for the moment. It's a completely other measure. This is the thing I mentioned to Justin, where we're measuring F1 score, but we're measuring it for node onsets and node offsets. Then we started to look at things together. This is essentially something that came out of Merle. They tried mixing deep clustering and mask inference, and they claimed that it was, in their Chimera paper, you know, they called it stronger together, and they got better performance when they used both. We did not actually see that in our work. So, but let's talk about mixing with transcription now. Transcription, when trained by itself, it got this F1 score of 0.37, and higher is better here. When we mixed it with deep clustering, it actually got slightly worse when we trained on both. When we trained with transcription and mask inference, so the other source separation approach, it still was slightly worse. But when we trained with all three, it actually got slightly better than training on transcription by itself. And so for us, at least in the results you're seeing here, and of course, you know, on a different data set, you might discover different things. But at least for us, what we found was that deep clustering did, when we used both mask inference and deep clustering loss together, it did improve transcription performance. Now, putting them all together did not make the system better at separation than using mask inference alone, but it didn't make it worse. So we thought, if on one task it's no worse and the other it's better, then great. And oh my God, did I not share the screen when I told you all that?
Yes.
You didn't.
Oh no, I feel so bad. Let me just briefly show you the screen and then you'll see. I'm sorry, someone should have stopped me when I was in the middle of that talk. Here we go. I got to the end of it and I realized I'm illustrating this thing, and we'll just jump straight to the punchline there. So if you can look at the bottom there, when we trained using all three loss functions, the results in red, higher numbers are better in all cases. The higher number is either when we train with all three, or it's tied with the best thing that any other approach did. And so I think that answers your question.
Yeah, thank you. That's super interesting.
And we're probably at the end of our time, so I want to let the next speaker take it away, because I want to hear about all this other work that's happening.
Thank you, Professor. Thanks a lot.
Thank you.
Our next speaker is Dr. Anna Huang, who is a research scientist at Magenta, Google Brain. Her research focuses on designing generative models to make creating music more approachable. She is the creator of Music Transformer and also the ML model Coconut that powered Google's first AI doodle, the Bach Doodle. She holds a PhD from Harvard. She spent the latter part of her PhD as a visiting research student at Montreal Institute of Learning Algorithms. She has been a judge on the Eurovision AI Song Contest. Her compositions have won awards, including first place in the San Francisco Chorale Artists a cappella composition contest. She grew up in Hong Kong, where she learned to play the gazang. And I want to share my screen to show what the gazang is. This instrument. It has like 18 strings. So please welcome Dr. Anna Huang, who's going to talk to us about Bach Doodle, which was made with the aim of making approachable music composition with machine learning at scale. Professor Anna, please share your screen whenever you're ready.
Okay. Thank you for the introduction. And it's really an honor to be here. And it's really nice seeing a lot of familiar faces and friends that I haven't seen in a long time. So this is great to be able to catch up. It makes me a little bit more nervous, but we'll see how it goes. And yeah, feel free to interrupt me with some questions. And then for kind of larger questions, we can talk about them after the talk. Let me see if I can do a sound check first, right after I share the screen. Okay, see, can you see my screen?
Yes.
I realize I can't see everybody when I'm.
Yes, we can see your screen.
Okay. Is there a way to see folks and my screen at the same time?
You should be able to. I think there's a little thing to see people. You can see either one person or multiple person or whole grid.
Okay, let me. Okay, I don't seem to be able to find it, but that's okay. Okay, I'll just try to imagine everyone's out there. And let me do also a sound check. Let's see. Can you hear the sound okay?
Yes.
Cool, awesome. Thank
Really?
you.
I can't hear it at all.
I mean, I can hear you.
I cannot hear anything.
No, I did not hear anything.
Okay, no, this we don't hear.
I couldn't hear it either.
Okay, so some people can hear it, but some people can't.
I can
I
hear
can
your
hear
voice,
you.
not
I couldn't hear that. Yeah.
Cannot be here.
You can't hear the music.
Okay,
You might need to turn on original sound.
Anna, you have to go, you know where it says start video?
Start video.
Yeah, on Zoom, start video, lower left-hand part of the screen, it should be for your Zoom.
I wonder if it's because I'm in the share screen
Okay,
setting.
good.
Okay,
Now,
let me get.
if you click on start video, the little arrow next to it,
Yeah. There's,
then you'll get up a thing for video settings.
yeah.
And then under that, there should be audio.
Yeah. there's the microphone and the speaker. Okay, I'm switching to the MacBook speakers as opposed to the AirPod speakers.
No, no, no. There should be a way in here to share your
Okay.
audio.
Let's see. Oops.
Oh, have they moved it? Oh, under advanced.
Okay, join audio by computer when joining a meeting. Okay, let me do a quick check and see if that worked or not. Can you hear the music now?
No.
No?
Also on the audio page, there's an advanced button where you can enable turning on original sound.
Let's see.
It's in the lower right-hand corner. It says advanced.
Lower right hand.
No, that isn't it. That removes echo cancellation.
Hey, Anna, I think under share screen, when you click that, once you click that, there should be something that says like
Share computer sound,
Yeah.
right?
Yeah, that's it. That one.
Yeah,
that
I think
one.
that's exactly it. Thank you. Thanks so
Yeah.
much.
and then you can double check the volume thing on your actual computer to just see that it says like Zoom audio. You should be good.
Ah, okay, let me, oops. Okay.
For the record, I've definitely had some computer audio canceled by the tonal cancellation, noise cancellation.
Can we hear the music
Yep.
now?
Yeah.
Okay,
Yep.
so, okay, I'll go back to the top. Sorry for the technical difficulty. I haven't used Zoom for a while. Let's see, okay. Maybe somebody warn me when I'm like 15 minutes in and I'll start wrapping up. Everything good? Seeing my screen and
Yes.
okay. Yeah, it seems like there's a huge HCI problem that can be solved, or me using the tools better. Yeah, so I'm excited to be here to talk about some of the music generation work I've been working on, and my background is both in college. I studied both music composition and computer science, and I always knew I wanted to combine the two. So a little bit of a story. Freshman year in college, I was really excited. Now I can finally have proper lessons to learn how to write music. But instead, we had these counterpoint classes where we were basically going around the class and looking at each other's assignment and trying to circle, like, where did we violate these counterpoint rules? So we didn't actually get to talk about music in the class and learn about how do we write down our ideas, how do we develop ideas. It was all about learning the rules. So as a computer scientist, I thought, okay, like we have this actually a book of rules all written down. Could I translate them into computer code? So that's what I did, kind of using the traditional AI approach of implementing expert systems. And the result was this GUI interface. It was written in Java because in the CS classes, that's what we were learning. And it's quite a kind of a text-based music representation where I implemented basically a grammar checker for music in the 16th century style of counterpoint. And it would highlight the mistakes that you have. For example, if you had parallel fifths, it would point it out. If you're doing a large leap and not like compensating it in the other, going in the other back in the other direction, it would point it out. So that was kind of my first exploration into kind of thinking about how we can use computers to help us when we're in the middle of writing music. Still, this was not yet generating music. So fast forward about 10 years, I was really excited that at Google that there's this Magenta project that just started out. So I interned with them when they were kind of launching their project. And it was a lot focused on using machine learning to try to kind of expand our creative process. So back then, we were still using kind of RNNs, LSTMs to generate melodies. And melodies are kind of the natural place to start because language has only one sequence, and melodies is like this one sequence of data that we could model. But I was thinking, what if we wanted to, I wanted to really generate full-blown music, like things that sounded like it was already complete. And so I kind of went back to what I was working on as my first project, the counterpoint. Like, even though writing a good melody is really hard, because in some ways it's under-constrained, but with counterpoint, we know about all the rules, how we can put the multiple lines together. And maybe that gives us a way where tackling kind of a more complicated, assuming more complicated problem is actually easier, because there you can always have something to anchor on. You're not composing from scratch, but once you put down something, you're trying to write the other lines and then rewrite your existing lines and try to kind of iteratively improve it. So that was kind of moving from modeling melodies to polyphonic music. And later on, the motivation behind this model was how can we actually use it in a generative setting where people are creating their own music, and this tool can kind of come in and help. So one of the applications was how do we create this delightful experience with the Doodle team and allowing a lot of people to be able to compose often for the first time and have a model help them create something more than they would otherwise be able to do. And so this project was the Bach Doodle, and it was launched last year to celebrate on Bach's birthday. So I'll talk about the model later, but first I'll give you kind of a preview of how that experience looks like. So on March 21st, the Google homepage was changed into this. And this is the experience.
All right, let's start with an E. E to G. Back to E, to D, C, and B.
So the user inputs a melody.
This sounds great. Now let's click the harmonize button.
So now the machine learning tries to figure out the other parts.
It doesn't sound too bad, right? It sounds pretty awesome. But now, how does it sound if we play these 4 voices on a guitar? On 4 guitars, let's find out.
So now he's playing just the computer-generated parts.
That is pretty cool.
So in 2 days, this harmonize button was pressed 55 million times, harmonizing all the user inputted melody. And people really had spent a lot of time with it, kind of playing around, and sometimes they would put in melodies that's like scales and see what the model does, and then kind of change around different aspects of the melody and see how the model reacts. So it really allowed a lot of people to have this kind of first-hand experience of interacting with a machine learning model and see how it can spark creativity. And so that was the kind of a summary of the experience. And now I'm going to go into kind of more of the technical part to show how were we able to do this. And the initial motivation of this model was that I wanted to create a machine learning approach that would allow you to infill arbitrary blanks. So imagine you're in the middle of writing music and you just have random things on the page, and you want the model to try to help you to glue it together so that you can see how it might look like when it's more complete and try out more ideas. The challenge was that usually how we would write down a generative model is that we would think of it as a sequential process, and we would generate note by note. So say there's 3 notes in the melody, we would first say like, okay, what are all the ways to start it? And then conditioned on the first note, what are the possibilities for the second note? And then conditioned on a longer context, how do you predict the next note? So it's by this kind of note by note forward process. You can imagine this is one of the possible orderings. Of course, you can generate the music backwards too. That requires that you train another model to have those different factors that goes backwards. And in cases, you can also have it embodied in the same model. But when it comes to polyphonic music, you have multiple instruments playing at the same time. So what is a natural ordering here? Like what we see is more of a grid. We might say, okay, like we want to think about melody, how the different instruments play their melodic lines. So one possible ordering is to go through all the lines kind of line by line. But this is a bit problematic because then the harmony is kind of becomes a second, taking kind of the backseat. And then whenever in the ordering things are far apart, it makes the model harder for the model to kind of model the dependencies. So then, okay, maybe another approach is to think about the harmony first, because like those are the notes that are sounding at the same time. And then the ordering would be to generate all the notes within a chord and then kind of progress in time. So in some ways, it's forcing us to make a modeling choice, and this is quite also a common struggle in music theory too, where when we do analysis, sometimes we have to kind of pick, oh, do we think about the linear versus the vertical relationships first? So our answer is, let's think about, at the end of the day, what do we want the model to be able to do? And that's being able to fill in any arbitrary gaps. So why don't we train it that way? So that way it can like fill in from scratch. It can do harmonization given a melody. It can fill in any bits and pieces. So that's how the model is trained, and the model is called Coconut because under the hood, this model is a deep convolutional neural network. The interesting thing about this model is not the network itself. The network could be any network. It could be a transformer, but it's how we train it through this infilling process, and also how we can generate from it. So why does this kind of masking of different parts of the piece allow us to learn a model that can do this very flexible infilling? So here we have a toy example where the first note is given, is observed, but the second 2 notes are missing or masked out. And the model is trained to do reconstruction. So by doing reconstruction, one factor it's learning is, given the first note, what are the possibilities for a second note? And this corresponds to one way of factorizing the joint. So the ordering here is 1, 2, 3, and this covers the second factor in that ordering. At the same time, when we're trying to do reconstruction, we're also learning, given the first note, what is the third note? So this actually corresponds to a factor in a different factorization of the joint. here the ordering is 1, 3, 2. So you can kind of see how this masking is allowing us to learn different parts of a probabilistic model. And in fact, if you do all combinations of masking the score out, for example, everything but 1, everything but 2, and in all places, then whenever you have an ordering that comes along, say 1, 3, 2, this allows you to have learned all the factors that can support that generation ordering. So for example, here we get the marginals, and here we get the conditionals. Okay, so that's how the masking allows us to learn this model that can model music in all permutations, basically, and factorial of permutations. So in terms of how we represent the music, it's a little bit like pixels. And we literally think about, say, the RGB channels of images as the SATB, soprano, alto, tenor, bass channels for the music counterpoint. And we do this generation actually through rewriting. So this is a harmonization that we're doing. The melody is given, and you see it kind of filling in the other parts. And instead of kind of picking and ordering and doing the generation left to right, maybe we'll see it again. It's kind of gradually settling into configurations, initially rewriting a lot, and later on just rewriting bits and pieces to fine tune, so that eventually you get something that's globally coherent. And this is when you play with the Bach Doodle, this is actually under the hood, the process that it's going through to give you the 2 bars. So what are some of the benefits of this approach? Which, if you follow some of the NLP work, this is also used in different ways, for example, in BERT and also in XLNet, where they do kind of the masking. It's a very kind of similar approach to this. One advantage is that you can think of it as a form of data augmentation. So if your data is quite small, set is quite small, or even if you have a larger data set, it just kind of allows you to learn kind of more robust features. And on the generation side, it allows you to really do this very flexible in painting through this rewriting process. And in a way, you're kind of learning a multitask model that allows you to do a variety of musical tasks kind of baked in one. Okay, so we worked on this model a couple years before the Bach Doodle came out. So initially, we didn't really have an interface to kind of interact with it. But a musician friend of mine was really excited about the model and said, like, could he write a melody for the model to harmonize? So I waited for many weeks, and this is what he sent me. So initially, I thought it was a joke, because we all know it's Ode to Joy. But later on, at the end, I heard there was this tweak. And then I realized it was quite a trick question. Because, for example, if the model was generating left to right, then when it approaches the ending and hears that it's quite different, it's going to be quite hard to change your course to fit into it. But because Coconut is this model that does rewriting from all directions, from forward to backward, backward to forward, up and down, diagonally, it's able to really work around it. So this is Coconut's harmonization. Okay, so that was Coconut, the model behind the Bach Doodle. Afterwards, we did some more study to try to figure out, is this tool really able to help novices, people who are more new to writing music? And we found actually there's still some inherent challenges. For example, the amount of music generated was quite a bit for somebody to digest at once, because you give it a melody, it suddenly gives you multiple instrumental parts back, and that's a lot. And also it's quite non-deterministic. You don't have a way to kind of control how the harmonization looks like. And every time, if it's not what you like, then you kind of click regenerate again and again until you find something you like. So it's really not the most kind of effective process. So I worked with an intern, Bryan, who worked with us last summer, and he built on top of Coconut, and he added a bunch of AI steering tools to allow people to kind of engage with the interaction with more control. So some of the examples is, for example, you can control which line you want to generate. So you can generate line by line, bit by bit, instead of like everything at once. You can also, you also have an example-based slider, which is if you have something, you can say, oh, I want something similar to this or very, very different from this. You also have knobs saying, oh, maybe I want something happier, something sadder, basically major or minor. And also you get to see multiple alternatives at once. So you can kind of do the search faster. And we found kind of comparing this Cococo to the kind of the older interface. For example, like the Bach Doodle like interface, people described like, oh, the AI was a brilliant composer, or it was kind of a take it or leave it. But with Cococo, they were able to really build out the music kind of bit by bit by themselves, and they felt like it gave them that they could actually adjust the generation to do what they wanted it to do. So you could try it out yourself with this interface at the link below. Okay, so yeah, that was a Kai paper that we have to kind of summarize the work. And I'm going to switch gears a bit, and I'm guessing I'm running out of time soon. And just briefly kind of touch on music transformer and show you some samples. And I think many of you are familiar with the kind of the self-attention kind of architecture. So I want to kind of bring you kind of behind the scenes and look a little bit more at how the self-attention is attending to structure, for example. So this is a piano roll of a sample generated by Music Transformer. And here I manually highlighted where the theme returns. So there's kind of a motif that returns throughout. It's kind of the broken lines that you see. And this is visualizing the self-attention on the last layer. The different colors are the different heads. So is there a question? Okay, so you see it attending to previous sections where the motif has occurred. And that's how it kind of builds up the longer term structure from scratch. So this is a visualization of, as the model is generating forward, what is the context it's relying on to generate the piece. I think there's a bit of a lag between the audio and the video. So that was the music transformer generating from scratch. There's also different ways to interact with the model. Ian Simon is one of my collaborators who worked a lot on this. And for example, you can give it a melody, and it can condition on that melody to generate kind of a piano accompaniment. The model was trained on a lot of piano music. And you can also give it a chord progression of, for example, an existing song, and have it render and how a pianist might play it. And finally, we, in some ways, so the music transformer is working on the symbolic level. It's not yet thinking about how the audio, or the performance on an instrument, how that sound is produced. So we actually kind of put it in a larger picture of thinking about, okay, how do we go from end to end, kind of from audio to audio? How can we take audio and be able to understand it through transcription, and be able to train on the transcribed music to get all the performance details of timing and velocity, and then be able to generate a new piece using Music Transformer, and then synthesize that MIDI into expressive audio using models like WaveNet. So the sample that you're going to hear next is generated using the procedure I've just described. So in a way, it's like end-to-end machine generated, but in practice, it's these kind of modularized approach put together as building blocks. Thank you for listening. You can check out a lot of the work and more samples and finish listening to that piece on our blog posts with all the projects. We have kind of a blog post for each to help you get the picture of it. And yeah, I look forward to your questions, and thank you again.
Thank you, Anna.
Just ask.
Perhaps if we could keep questions for Anna in the chat, or maybe for the networking event. Anna, I hope that's all right.
Yeah, I think I probably took a little bit more time.
You're not too far off. It's very close, so you're fine. I think at this point, I will introduce our last speaker. His name is Hanoi, and he is also a research scientist at Magenta, Google Brain. But you must be wondering why Hanoi. Hanoi is not his real name. He's called Hanoi after the city, which is in Vietnam, I think. That's because his parents fell in love there, and they named him after that charming city. So to tell you more about him, he was born and raised in Bangkok, Thailand. He's currently a AI resident at Google AI. His research focuses on robust neural audio synthesis, rendering audio and music with machine learning models. Hanoi holds a degree in applied physics and music composition, both with distinction from Yale University. In his MSc at Georgia Tech, he developed machine learning models for an ultrasound sensor that enables an amputee to perform high dexterity tasks like playing the piano, an impossible feat using today's sensors on conventional prosthetics. He also writes music under the moniker of Yabao Hanoi, so please check that out. You can find his tunes on Instagram at Yabao Hanoi and Spotify. So today, Hanoi will talk to us about differentiable digital signal processing, or DDSP.
Cool. Can everyone hear me?
Yes.
Great. Thank you very much, Arshiya, for the introduction. Thanks to all the other speakers and everyone for being here today virtually. Super excited to be talking to you all about some recent work that I've been working on called differentiable digital signal processing. I'm going to share my screen and just going to do a quick sound check. Let's see, can you hear this? Can people hear that?
No.
Okay, I need to do the same thing that Anna did, so hold on. And share screen. Oh yeah, optimize screen share for video clip, share computer sound. There we go. Okay, let's try this again. Great, perfect. Okay, and I'm also gonna start a timer on my end. Cool. Great. Okay. So it's great to see a lot of familiar faces in the audience too. And I think one of the co-authors of the paper, Adam Roberts, is also on the call. So I'm going to be talking about differentiable digital signal processing. This is a work from the Magenta team that we just published recently in iClear, and it's also an open source library on GitHub. So this is work with Jesse, Chenji, and Adam, and my name is Hanoi. So super quickly, you've already seen the talk by Anna. Magenta is an open source research project exploring the role of machine learning in the creative process. This is actually a nice complement, a nice counterpoint, no pun intended, to Anna's talk. In Anna's work, you can see a lot of the research at Magenta that looks in music generation from a symbolic domain and making sense of music in the symbolic domain. DDSP is some complementary work on the other side of the spectrum, which is looking at audio synthesis, which is another very important part of research in Magenta. A little bit about me before we start. My name is Hanoi, named after the capital city of Vietnam, but I am from Bangkok, Thailand. And I come from a background in physics and music. Was at Yale, then Georgia Tech. I design musical instruments. I compose music. I go by your boy Hanoi. And I also, I'm very passionate about the intersection of audio machine learning and digital signal processing. So what is DDSP? DDSP is an open source library that fuses interpretable signal processing with the expressivity of modern neural networks. And what we're going to do in the rest of the presentation is unpack what that means. And I have a lot of audio demonstrations sort of lined up, queued up to unpack this further. But before we start, there's a really fun video that I'd like to share with you that literally explains what DDSP can do in about 20 seconds. So let's start off with that. Bow wow wow wow. Cool. So one of the things that our technology lets you do is basically do like very, very high fidelity tone transfer from one audio source into another. This was a very fun Twitter post that I did a couple of weeks ago. So let's set the stage before we talk about DDSP. I'm going to be motivating a couple of problems that we in the audio signal processing community often find ourselves trying to solve. So for example, in audio analysis, given input audio, extract the fundamental frequency of the audio. So if you have someone singing, your task is to extract the fundamental frequency. Another problem in a different domain might be something like audio effects. So if you're given a chain of audio effects, you want to find the coefficients that maximize some kind of loss on a particular task. So let's say you want to separate speech from noise. And another problem, audio synthesis. Given some source audio, such as the following violin, you want to learn a model that can generate more audio that essentially sounds like the source. And so we all know that these are problems that we have solutions for using digital signal processing. And there are time-based approaches at solving all of these problems. There are spectral-based approaches. at solving these problems. And what we just need to do is basically find, search, or hand tune, or optimize the DSP coefficients. And as you know, this is very efficient and it works. But very often, if we look back in history, some of these approaches can be a little bit brittle. So if the signal has too much noise, for example, the fundamental frequency extraction can break down and things like that. With the new machine learning and deep learning revolution, we would now just say, well, you can just throw a deep net at it, which is true. And using a completely deep net approach is a very, very powerful approach. And it's a lot more flexible. However, there are some trade-offs. For example, machine learning systems require a lot of data and unfortunately are also black boxes. So just to remind you, audio as a machine learning problem is a very, very difficult task because, well, audio is a very, very long sequence. As you know, if you have audio for 3 minutes at 44 kilohertz, that's 10 million samples that has to be modeled. And some of you may have heard of WaveNet, which is one of the state-of-the-art models used for audio synthesis. And literally WaveNet just goes through and outputs each of these samples one by one by one by one. And it's currently powering technologies at Google, like the Google Assistant. However, as you know, WaveNet takes hours and hours, thousands of hours of audio, for example, speech, before WaveNet can actually start rendering high quality speech. And most importantly, these hidden layers that you see here are all black boxes. Like once the model has been trained, there is no explicit way for you to go in and say, WaveNet, I need this particular sibilance to be reduced here. There's too much high end in the sibilance. There's no explicit way of doing that because all these hidden layers are all black boxes. So there are other problems too that arise if you use only a pure machine learning approach. A really good example is here on the right. So I'm showing you 3 different waveforms, and I'm going to play the first waveform. I'm going to play you the second waveform. Oh, can't. Hello, there we go. And I'm going to play you this waveform. Now, those of you who are listening will say, well, those sound exactly the same. And they are exactly the same. Because as you know, for example, human hearing is phase insensitive. It's not sensitive to phase. But if you look at the waveforms, they're completely different. And to WaveNet, these are actually 3 completely different modeling problems. And so whilst it is sufficient that WaveNet can generate these waveforms, it's actually not the most efficient way of generating waveforms. And if you look at spectral-based approaches, models that, for example, generate spectrograms, you're limited in resolution, for example, by the spectrogram. And as we know, spectrograms aren't necessarily correlated with how humans perceive sound. In the case of strided convolutions, each of those convolutional blocks, has to learn every single variation in the waveform when it's trying to print the different waveforms and trying to align the waveform together. And as you know, human ears are very, very sensitive to discontinuity. So if one of these convolutional kernels just misses the audio by a slight bit and there's a discontinuity, we hear that as a pop. Also, a lot of these are not streaming real time out of the box. So we have really good priors about DSP and audio. So the idea behind DDSP is, why don't we integrate them with deep learning and essentially get the best of both worlds? The efficiency, the interpretability of traditional signal processing, but the flexibility and expressivity and nonlinearity of modern machine learning. Now, in order to do this, there's a couple of steps that have to happen first. All of modern deep learning is based on the fact that the functions are differentiable, and which means that you can compute a gradient and you can pass this back through the network and backpropagate it and use this as a loss signal to update the weights. And as you know, DSP is traditionally not formulated in a way that's differentiable and therefore has not been integrated into a machine learning pipeline end to end. So that's exactly what we did in this paper. And what I'm going to first do is introduce you to the different building blocks of DDSP. So we're going to motivate this from the perspective of audio synthesis. And we're going to start off first with your additive synthesizer. So just your plain old, very, very boring sounding additive synthesizer where you can essentially just specify different, oh, I hate it when this happens. I can't play this. There we go. So not very interesting audio. And then you can sculpt this with an amplitude contour. And then if you shift the harmonic distribution, then you can change the tone. So what's happening here is this is a component that has been written in TensorFlow so that gradients can actually be passed through the following equations that describe the different harmonics. And so to make this concrete, instead of a machine learning model, for example, synthesizing the audio directly sample by sample, what it's actually doing is it's outputting a matrix, which is a control signal to this particular signal processing model, signal processing component. So a concrete example is a matrix that's 250 by 81. 250 refers to the time steps, and 81 refers to one coefficient that controls the overall amplitude at that frame, and then 80 coefficients specifying how overall amplitude is divided between harmonics. So the machine learning model is spitting out these control signals, and then it's the signal processing algorithm that then renders the audio. We also have a filter, and this is a linear time varying filter where the model can essentially specify the transfer function, the magnitude function, and we use the frequency sampling method to invert this into an impulse response and then convolve that in the audio. And what this allows the model to do is to actually specify very expressive and time varying filter. So here is an example of this filter that you see here being filtering on white noise. Oh, excuse me. So at every time step, the machine learning model is outputting essentially what the magnitude transfer curve of the filter needs to be. And then lastly, we also have a reverb, which is an impulse response. And in this case, it's just a very, very long 1D kernel. So we are going to show you how DDSP works in the domain of audio synthesis. It can be used in other domains, but just to ground our conversation, we published our paper in audio synthesis, which traditional machine learning models, for example, and show how it works in that domain. So in this case, our model looks something like this. This is a simplified version of one of the experiments that we did, and I'm going to quickly take you through the different components of this model. DDSP refers to the parts in yellow. So as you can see here, this is your reverb with your filtered noise synth and your additive synthesizer, and it's composed together very much like how you would compose together a signal processing chain. Remember that the DDSP components don't hold weights. They are simply signal processing algorithms that have been written in TensorFlow, and thus you can pass a gradient through it. The decoder itself is where all the weights are, and this is your machine learning model. But we want to highlight that the machine learning model itself is super, super basic. It's just a bunch of fully connected layers and an RNN. There is no sort of special tricks that we did in the model to do the synthesis. And we really did this to highlight that it's actually the combination of the priors that are built into signal processing algorithms combined with the machine learning model that lets you efficiently generate the audio. And it's not because we have an overpowered machine learning model that's able to generate the audio with such high fidelity. And so when we train the model, we train it like an autoencoder. So, you know, the target audio comes in here, and the conditioning signal that we pass to the decoder is actually the fundamental frequency and the A-weighted log amplitude of the audio. So just to make this really concrete, if this was your training data, we extract the fundamental frequency, which is what you see right here. So that's like a 1000 by 1 vector. And then we also extract the amplitude. In this case, we call it loudness because it's an A-weighted log amplitude. And I want to highlight that the model only sees these two low-level descriptors. The model is not given any spectral features when it's being trained as this autoencoder. So the decoder only gets to see what the fundamental frequency is and what the loudness is. And using that information, it needs to output the right control signals to the DSP components to synthesize the sound of the violin. Yeah, and when it synthesizes the sound of the violin, we use a multi-scale spectrogram loss, so just essentially an STFT with different window sizes, and we compute the loss between the synthesized audio and the target audio, and we backpropagate that to update the weights in the decoder. So just to make this concrete, what I'm going to do is play some audio examples. So let's say this is your training data. It sounds like this. we extract the fundamental frequency, amplitude, the decoder reads this, it outputs the control signals into these DSP algorithms, and then it synthesizes the audio. And so when it first starts, it sounds terrible. Right? That totally sounds like a bad synthesizer. But then you let it train for a little longer. It's getting better at 100K steps. Sounding more like a violin. And by the time it finishes training, the model is able to output control signals to an additive synthesizer, the filtered noise synth, and the reverb in such a way that it's now indistinguishable from the original audio. And so there are some really fun things that you can now do with this. So if we have, for example, this is the original audio that's being played, we can now actually tell the model, because it understands what the reverb and impulse response of the room is, you can actually just ask it to play without. You can do it without the reverb. You can also ask it to play the filtered noise component. So this is like literally just the sound of the friction. And then you can also ask it to just play the harmonic component. So this is like the pure sinusoidal component. And then coming to the demo that we showed you, fundamental frequency and amplitude are physical quantities that have interpretable meaning to like humans and also just the physical world. Like these two quantities are things that have physical meaning in the natural world. And you can extract fundamental frequency and loudness from other signals. So here is an example of someone singing. Somewhere over the rainbow. And then we can extract the fundamental frequency and the amplitude. Of course, we have to transpose the F0 to be in the range of the violin, but then you give that signal to the violin and it will do this. Cool. And what's really exciting is this model was trained on the Bach partita that you heard in the previous slide. So it was never, all that it knows about the violin is this 10 minutes of audio that it heard from this particular CD. But you can hear that it's actually pretty robust and generalizing to a completely different signal, in this case, me singing, and sort of retaining the tone of the violin. And what's great about DDSP is that it's very, very fast and it's very lightweight. So that demo only required 10 minutes of violin and flute to train the autoencoder instead of 1,000 hours, used by WaveNet. It's very fast to train. You can train this particular model in 3 hours on a single GPU, and we can also do 1 hour on a TPU. And it's really fast to render audio. So the offline Python version can generate 10 seconds of audio in about 1 second of compute. Actually, it's now faster in TF2. That should be like 0.3 seconds. And you can also try this in the public collab. We have a collab where you can actually sing into the collab and poke around at the model and try this yourself. And I'm going to play you this demo, which is one of my favorites from some of the sound design that I've been experimenting. So what we're now going to do is we're going to take as input the sound of a zebrafinch, which is a bird, and it has a very, very distinct, very unique way of, it has a very unique bird call. So what we can do is we can train a DDSP model on a flute. So this is a Bach flute sonata, but now we can ask the model to re-render the zebrafinch, but with the tone of a flute. So I'm going to stop it there. This is actually sort of the demo that I think really is the exciting demo that shows you why DDSP is so powerful, because this is actually kind of non-trivial if you think about it. If you wanted to design this using pure DSP, you would need to handcraft a lot of coefficients for the flute and for the zebrafinch, but now if you wanted to switch the instrument or switch the input, you would need to come up with a whole different way of doing it. And pure machine learning requires way more than 10 minutes of flute in order to be able to train this model. You can also do the same thing with saxophone. And here's the re-render. So my favorite part here is you can even hear the sound of like the person like flapping on the saxophone itself. So I see that we're coming to 20 minutes, so I might just stop the presentation here, and I have some extra slides. So it might turn out that when folks are asking questions, that we'll get to some of those slides. But the important thing is that, but wait, there's more. We have other signal processing elements that have already been implemented in the library, like vibrato, flangering, chorus. We have wave shaping, subtractive synthesis, wavetable synthesis, and we're really hoping that by open sourcing this, people from the DSP community can contribute their own particular areas of expertise to this particular library. I'm going to skip to the end of my presentation. And before I do that, the exciting thing is because the signal processing elements are interpretable, right? Like you know what to do with a convolutional kernel. You know what to do with a magnitude response. Once the decoder has been trained, you actually don't need to use DDSP to do the synthesis. Like you could actually swap this out with a juice implementation of an additive synthesizer and a juice implementation of a convolutional reverb, and just use the decoder part in, for example, TensorFlow Lite. And the decoder part in TensorFlow Lite can actually be called in real time in a real-time audio thread. And then you can do the synthesis in real time. We have some friends from IRCOM who actually like re-implemented our paper before we even open sourced it in PyTorch, trained their own model, and actually made it work in real time using pure data. So I'll just play a quick part of that. Ooh, why is that not playing? Hello. Maybe I have to go into presentation mode. Just give me a second. Okay, not too sure what, oh, okay, let's try that again. Let's see if I can play this. Yeah, here we go. So just in the interest of time, I'm going to stop it there. But what's happening there is they trained the model, they took away all of the PyTorch parts except for the decoder, and then they're using the harmonic synthesis. They're using an additive synthesizer that they wrote themselves in pure data to do the processing. We still have things that we still need to be solved, and so if you're in the audience and you want to take a little bite at solving some of these things, like we don't have a good way of training IIR filters yet. And how to deal with feedback in signal processing chains. And with that, thank you very much for listening. I'll leave some room for questions. Questions from the, oh wait, am I missing questions? Hold on, let me just stop my screen share. Am I missing questions from the chat?
I think there's one question.
If we're allowed to just talk, boy, I've got some questions. Hanoi, great to see that you're doing, yes, great to see that you're doing great things at Google, and even greater to see that you're doing great things with audio synthesis, my love.
Yeah.
Yeah. So tell me a bit about the filtering piece, the filtered noise. And you just said some of it with needing better IIR training, IIR filter training. What is that filter model currently? And yeah, give us a bit of background on that.
Sure. Let me go back and actually recast. So what's going on? So what's going on here is wait, why can't I click this? Okay, so what you see here on the left is a oh, we should sorry, this is not labeled. So you see frequency on the bottom and amplitude on the left. So this is just basically a low pass filter. And so what the model does, well, the way that we've set it up is the model specifies a magnitude response at every time step. So here, for example, if it's a 250 by 120 matrix, what that means is that there are 250 frames in this audio. That 250 frames, if it represents the number of time steps, for example, in a second. And then at every time point, the model essentially just outputs like on like a vector of 120 numbers, which just refers to this particular transfer curve here, spaced out across the frequency spectrum. Everything's at 16 kilohertz. So that's why it goes up to 8,000. And then what we do is we take the IDFT. So this is basically just implementing the frequency sampling method, and we get the impulse response of that. And then with that impulse response, for that particular frame of audio, we basically convolve that over with white noise, and then we do the same thing. So we move on to the next time step. We find what the impulse response needs to be for that frame, convolve it with white noise, and then that's the noise signal for that particular frame in audio space.
Okay, and you're doing it just like what you said, convolving an FIR filter basically that you've brought back over from the frequency domain. You had mentioned IIR filters there. Is this something for future work, or where does that come into play?
Right. So this is actually a problem that we don't know how to solve yet, and this is actually something that we would love for folks in the community to help figure out. When I gave this presentation at Native Instruments in Berlin, that was also the first thing that Julian Parker said. It's like, how do we do IIR filters? And we had a great conversation about how to do that. But there's no good way of implementing IIR filters right now. I can talk a little bit about why that's the case. So an IIR filter looks a lot like an RNN, right? Where its current output, depends on what is outputted in the past. In the case of RNNs, what we do is we, roll them and we fix it at a particular time step. So like 32 time steps into the past. And a lot of really smart engineers at TensorFlow have basically figured out really good ways of optimizing that computation on GPUs and accelerators, so that when you unroll that time step, right, you can train and backpropagate the weights in that time-rolled fashion for an RNN. What hasn't happened is we haven't sat down with a bunch of audio DSP people to say, well, how do we do the same thing but efficiently do it for an IIR for an IIR filter without doing the sample generate, save the output, generate, backpropagate, and do all of those things in a non-sort of optimized way. So if I understand correctly, at least from when I was talking to Jesse and the TensorFlow team, it's like it would require like some careful thought on how to efficiently implement an IIR filter so that it can train on an accelerator.
Okay, fair enough. Yeah, and not as much as you'd think, but we'll talk more.
Yes.
This is very cool, though. I mean, I'm sure everybody else is going to say it too, but man, this is very cool.
Thanks. Yeah, it's all open source, and we're just really stoked to see what people do with it and contribute to it. Like, we've gotten a lot of pull requests to add new functionality and things like that. So yeah, if you know how to do the IIR part, we should talk about that.
And we will.
All right.
This is Bryan. Awesome talk. Two questions. I mean, obviously exploding gradients in recurrent, well, basically, when you were talking about feedback, it does seem to be the issue here, that everything you think about with recurrent nets is how to make sure that, as time goes by, things shrink instead of grow. Otherwise, you run into a problem. And feedback seems the opposite of that. But I'm just wondering, so my student, Ethan, will be at Google this summer. And so I'm imagining a fun demo where you could take Cerberus peel apart some stuff and hand some parts of it to Anna's work, have it be reharmonized. So you could take Beatles' Oh Darling, have it reharmonized along the lines of Bach, and then have it tweeted by a chorus of birds. And you have all the parts right now to do that. And I'm just encouraging you to get together with Ethan over the summer and make that happen. I think it would be awesome.
Yeah, that's actually, I'm really glad you brought that up, Mr. Pardo. I'll definitely reach out. I think he may have already, like, has he, if he's already started, I think I might have gotten an email from him already in my inbox. The name is very, very familiar. But I think your question also points to another very exciting use case of, you know, a technology like Cerberus, a technology like some of the transformer generation that Anna has been doing, and also DDSP, is that there are ways to get all these different models to talk to each other, actually. So one of the active areas of research that we're doing right now at Magenta is essentially the DDSP model requires a continuous fundamental frequency contour. It can't take like discrete MIDI notes, but we have ways of basically training that allows the model to basically be fed just like discrete MIDI notes, for example, and then it will try to infer, you know, how it needs to synthesize this audio if it was actually being played continuous, if the fundamental frequency contour was continuous. That's something that we're actively working on right now. And it would enable, you know, these different symbolic systems to talk with audio synthesis and actually have them, you know, for example, be trained end to end and all wonderful things.
Well, you could just run source separation though, like Cerberus also outputs that. Fire it through Justin's crepe model, or maybe that newer Spice model to get your F0. And so it would still be possible to hand you that continuous control.
Yeah, definitely. We're thinking from the perspective of like, it's definitely possible to use it in its form right now in terms of getting continuous fundamental frequency contours. But we're also thinking about the case where like a musician, you know, is hitting on like a discrete input method, you know, on a keyboard, on a website or something like that, and sort of allowing the model to be able to parse and interpret discrete events, but then infer what the continuous events need to be from that to make the model as expressive as possible. But yes, you're totally right. With the source separation and Spice and F0, it's totally doable. Actually, we have, so that video that I showed you at the start was like a video that I posted on Twitter. And some of the responses that I got was actually really cool. Like someone actually took a Spleeter, ran it on Lady Gaga, took the Lady Gaga's voice, resynthesized it as a flute, put it back into the song, and then re-uploaded it. And it's like this cool Lady Gaga flute song where the lead is now a flute instead of Lady Gaga's voice.
So, yeah. Hi, Hanoi, great talk. I just wanted to clarify this resynthesis. So you basically have the fundamental frequency and the amplitude, and then the Z vector, the timbre vector. So is this basically taking, for example, the fundamental frequency contour and the amplitude contour of the bird, and then using the Z vector of the saxophone to get that example?
Right.
Okay.
No, not really. So the architecture that I showed you is one of the architectures that we did experimentation on and reported results for. And so this was specific to this idea of training on a very small data set and having a very expressive decoder that sort of, in a way, it's just like optimized for that one sound. What you're seeing here is a different experiment that we did where we said, okay, well, if the model can do that, if you now train your target audio across a wide data set of sounds, so violins and flutes and saxophones, then the model can learn to factorize information about timbre at a given pitch and a given amplitude into a compressed latent Z. And then in this case, if we modulate Z, then you can go from the sound of a trumpet to the sound of a mallet or something like that. But in this case, you obviously need the full data set of all these different instruments. So in the case of many different instruments, we show that you can do that. And in the one that I showed you before that's sort of yielding all these really fun results, it's the one model architecture that we created that was sort of designed that we had in mind, like people would be able to collect 5 to 10 minutes of something, train a model on it, and then be able to drive it with any other signal in a very, very fast and efficient way.
Mm-hmm.
Yeah.
Great, thanks.
I have a question that might be related to that, and also related to the first question that was asked. So when you mentioned these other DSP like analysis methods or other algorithms that can be implemented that you're interested for like other people to try out, is that, so that portion is related to what's going on or what's being learned within this Z block? Is that correct? Like where that incorporation of, like I'm thinking of like, in my specific case, like an analysis metric, like related to the voice. Like if I wanted to incorporate something about voice quality,
right?
It's trouble to map the parametric estimation back to a resynthesis method, like how I can incorporate something like that.
Right. So if I understand correctly, are you using something like a parametric voice synthesizer? Is that kind of like what you're trying to do?
So something, I guess I'm trying to create something like that. So like resynthesizing like attributes of the voice that we have metrics that are really good for analyzing those properties, but integrating them back into something that isn't the voice is like not really known. Like you said, like, would have to be very handcrafted at this point.
So I'll answer that by analogy first. So another way that you could have trained this model was to get rid of Z and get rid of this MFCC encoder and just gave it like spectral centroid or something like that. And so you have fundamental frequency and loudness, which are continuous vectors, and you just have spectral centroid. And the decoder will learn to take spectral centroid as a third input and use that to generate all the coefficients it needs to do here. So the idea there would be if you held pitch and loudness constant, but then you started to modulate the spectral centroid, the model will, like, it will change the output sound based on how the spectral centroid was shifting in the original data set that you gave it. Does that answer your question? So I'm sort of using the spectral centroid as like a placeholder for maybe some of these vocal features that you're talking about that make a lot of sense in analysis.
Yeah, exactly. Thank you so much. Super helpful.
Cool.
Yeah, hi Huang and Anna as well. I mean, this query is very small query, and I just want to confirm basically, how do you see basically the generative models, especially the GAN? How do you see in terms of music generation? Is it going to be, I mean, yeah, the first paper came, which is, and it was a very, I mean, cool papers, MuseGAN, that paper was the MuseGAN multi-track piano, it was generated. So I feel that when I have worked on GAN, so basically I feel that when I was basically generating the short period of a very short 5 to 10 seconds, it was, I mean, aligning in a very good way. But when I was expanding that time, at the time, I think it was not generating the good results basically. So how do you see GAN still, I mean, in terms of, you know, generating the good music? Yeah. Can you, I mean, give,
Yeah. So there's a lot of, there's a lot of different ways of generating audio, and GAN is one of them. MuseGAN is a good example. GANsynth from the Magenta team is another good example. And they all have their different strengths and advantages. So as you know, GANs go back to this idea of being like the hidden layers in a GAN. So like if I go back to this diagram right here, you can think of this diagram as essentially representing a GAN, right? Where you have a random vector Z that basically is convolved back up into whatever you want to have as your output. So GANs work really well. Like GANsynth showed that you can do that in a very, very good way. And so the way that I'm gonna answer that question is to say that in this particular case, DDSP allows you to factorize all the different components that go into synthesizing a sound into its explicit DSP components. So for example, it factorizes the impulse response of the sound into the reverb, and it factorizes the non-harmonic sounds, the noise, into the filtered noise. If you had a GAN, for example, it just renders all of this in one go. Like there's no disentanglement of these different things. However, where GANs will outperform DDSP is in the fact that one of the things that DDSP is limited by right now is we only do windows of 4 milliseconds, I believe. So if there is a transient that is shorter than 4 milliseconds, DDSP can't render that right now. You would have to reduce the time span. Whereas if you had a GAN, for example, that was generating spectrograms, it can actually generate these very, very sharp transients a lot easier than DDSP. So one interesting approach that you can have is, because you can linearly sum audio together, you can actually train a model, for example, that uses DDSP and GANs at the same time, such that the model essentially offloads the generation of very difficult transients to something like GAN or WaveNet, but it gives a lot of the harmonic components, for example, to DDSP, because those are things that actually like represent the periodicity of audio that's found in like the natural world. Does that kind of answer your question? Oh.
Hey, Hanoi, what do you think about having an output that's the length of the window? Could you train on that?
Having a output that's the length of the window. Which window are you referring to?
The time domain window. So it'd be another synthesis parameter for the additive synthesizer. Instead of just being a fixed 4 millisecond window, it would be a variable window that the decoder would output, and you would just adjust say the hop size is always half a window, whatever it is, or a quarter of the window.
Yeah, I guess you could do that. The only problem is if you have a variable sized window. So one of the things I'm doing right now is trying to run this in real time and actually have it, audio buffer in, decode, audio buffer out. If you're having a variable size, oh no, you'll still be fine. You'll just have to keep track, like, every time your audio buffer goes through, you just keep track of like where you're synthesizing. I guess you could do that. The only problem is deciding, training a model to decide the variable length of those windows, like, is a hard decision. So we would need to find a way of making that hard decision of like, you're gonna stop here, a differentiable function, essentially.
Yeah, it wants to be selectable. Like MPEG just has like 2 window sizes, like 256 and 512 or something like that. And so you normally have like a discrete set of choices. And so instead of differentiability, you would just have comparison. Interesting.
Hi, Hanoi, could you go back to the architecture slide one more time?
Yeah, sure. Which one? The big one or the small one?
The one that includes Z, I guess.
Yeah, sure.
Or I guess, actually my question doesn't particularly matter to either of those. I just wanted to double check, does the reverb yellow box at the end of the model, is that using the DDSP core frequency underscore filter function?
No, it's actually using under the hood. It's just a 1D convolutional kernel that has a length of 64,000. Yeah, it's literally just your regular like TensorFlow convolutions.
Oh, okay. One thing that would be great is if like all of these yellow boxes, I guess maybe for the wiki or for the GitHub or something, you could explain like where it maps to in DDSP, just to double check. But
sure. Yeah. Thanks for the feedback. I also would want to be wary of time because I think like we're definitely over the 10 minutes of questions allocated to this presentation.
That's right. But thank you so much for the presentation, Hanoi, Anna, and Professor Bryan.